Signal conditioning and the difference amplifier, especially the instrumentation amplifier. It has 3 op-amps, is available in a single IC chip. It has the very high input impedance, high voltage gain, and high common mode rejection ratio, and the higher the better. As mentioned before, it consists of 3 operational amplifiers, and if you look at the circuit diagram here below, you can see those 3 in the diagram, where the first stage has A1 and 2 that are connected as inverting and the non-inverting amplifiers, and in the second stage you have A3, which is connected as a differential amplifier and is within the dotted orange line. Now, to understand how this instrumentation amplifier works, let's try and analyze the second stage, which contains A3. Now, if we consider the ideal operational amplifier, we can say that there is virtually no current passing through the inputs of this stage, and then we can say that the current through resistor R4 and 5 is equal. And using Ohm's law, we can say that the output of the first stage, A1, minus the potential at node X divided by resistor R4 is equal to the potential at node X minus the output voltage of A3 divided by R5. And we also can say that the differential input to the A3 is virtually 0, so that we can say that the potential voltage at node Y and X is equal. And so we continue to the definition of how to calculate the output voltage of this stage, and we can end up with saying that the gain of the non-inverting input times the potential at Y or node Y minus the gain of the inverting input times the output voltage of A1 gives the output voltage. And if you need to understand this, you can try and compare it with the theory for the difference amplifier, and also how to find the gain for a inverting and non-inverting amplifier. With that in mind, we jump to seeing that to find the potential voltage at Vi, you need to consider that resistor R6 and 7 make a or form a potential divider for the output voltage of A2, and then we can find the voltage for drop over the potential voltage at node Y, which is the ratio between R6 and the sum of R6 and 7 times the output of A2. And with this we can replace Vi in the equation for the output voltage and end up with this equation. And you should try and see if you can come to the same conclusion. And if we continue this analysis and want to find a common or equal multiplying factor for the 2 inputs of the A3 by suitable choice of resistance values, then we can have this one where we have the gain factors of 1 plus the ratio between R5 and 4 is equal to to 1 plus the ratio between R7 and 6 times the ratio of R5 and 4. where R4 divided by R5 is equal to R6 and divided by R7. No, let's keep this there and just continue to analyze the first stage with A1 and 2. And we want to consider each output to be acting alone, and then we add them to obtain the overall response. This is called the superposition method. And for this, we can see that the non-inverting input of A1, that the difference signal V in 1 is the input, and that we have the gain factor is 1 plus the ratio between R3 and 1. And for the inverting input of A1, we have the input of V in 2, and so we can find the gain to be the negative ratio between R3 and 1. And with this, we also know that the common mode voltage on the non-inverting input is amplified by A1, and so we want to write an equation for the output of A1. End up with this equation. We have the differential gain times the differential voltage plus the common mode gain times the common mode voltage. And we can apply the same method to get an equation for the output voltage of A2. And now that we know how to find the output of A1 and 2, we can find the difference input for A3, where we subtract these from each other and get this big equation here. And as an exercise, you should try and see if you can get the same result for the difference input to A3. Now, if we have a special case of where R2 is equal to R3, then the common mode term disappears and leaves only that the difference voltage to the input voltage to A3 is equal to 1 plus the 2 times the ratio of R2 divided by R1 times the difference between V in 1 and V in 2. And again, as an exercise, you should try and see if you can get the same result. So with this, we can say that the overall gain is 1 plus the 2 times the ratio between R2 and 1. And in design, you would use R1 to determine the gain. Now, as an example of a differential or instrumentation amplifier, then here is the one. There is a general purpose instrumentation amplifier, which with the name Burr-Brown, number YNA114. This one has input impedance is around 100 gigaohms in parallel with 6 picofarads. It has a common mode input range between plus minus 13.5 volt. It has the CMRR of 90 decibel to 110 decibel, and the gain is ranging from 1 to 10,000, and the error is max 2%. And the output of this circuit is plus minus 13.7 volt if you have a supply voltage of plus minus 15 voltage. The gain is set by connecting an external resistor RG between pin 1 and 8, and to calculate what the gain should be, and then you say that it is 1 plus the ratio between 50 divided by RG, when RG is in kilo ohms. To understand this equation, you have to find the datasheet, which would tell you that it is because of the two internal feedback resistors.